I'm going to look back at this equation here. Let's look at that again. We could say 2021 equals K 2020. And now, I guess maybe I should write it one more time. B 2020 minus D 2020. I'm going to rewrite this thing as a multiplication problem. As a multiplication problem, what I'm going to do is I'm going to take the population in the year 2020, and I'm going to multiply it by 1 plus this, B 2020 divided by K 2020 minus capital D 2020 divided by K 2020. So this is now a multiplication problem. It turns out that we're going to do this so often that we give this thing and this thing a special name. Now you can see it's the ratio, this first one, this is the ratio of births that occurred in 2020 to the population in 2020. And this one is the ratio of deaths in 2020 to the population in 2020. So this happens so often. This thing, you will not be surprised. We're going to give this thing a name. And this thing is going to be very close to, this is just a ratio. This is going to be very close to the birth rate in the year 2020. And this thing is going to be close to the death rate in the year 2020. I think next lecture, either next lecture or the lecture after that, we're going to go into why I'm saying close to and not exactly equal to. We're going to be much more formal in one lecture about how to exactly calculate these rates. But for now, bear with me. I'm just going to refer to that as the birth rate and the death rate. And we're going to explain later exactly what I mean by that. So this birth rate, you will not be surprised. We're going to give it a special symbol. So I'm going to say this is now a K 2020 times 1. And I'm going to say lowercase b 2020 minus lowercase d 2020. And now this is equal to B 2020 divided by K 2020. And this is D 2020 divided by K 2020. So now we're calling this thing the birth rate. This is the death rate. And this is a common notation I use. I use uppercase. I use big B. That's actually the counts of births. And I've used lowercase b to mean the birth rate. So I'm not always consistent, but I try to be, and I fail sometimes, but I try to be consistent. I'm going to use capital letters, the majuscule, for the counts of things. I'm going to use lowercase b to mean the rates of things. So it turns out that this combination of b, lowercase b minus lowercase d, that happens quite a bit. It happens so often that we give a special name and a special symbol to that. So it turns out that B and D occur together so often that we give B minus D a name, a special name, and its own symbol. And it is that B minus D, we're going to give it the symbol lowercase r. And we give this thing a name. This thing is, let's come back. This is what we're calling the crude rate, this is called the crude birth rate. This is going to be called the crude death rate. And B minus D is going to be called the crude rate of natural increase. So lowercase r is our crude rate of natural increase. Let me rewrite now our original equation. It is K 2021 equals K 2020 times 1 plus B minus D. And that's going to be K 2020 1 plus R. And I think this was B 2020 and this was D 2020. So this is R 2020. And this is our multiplication problem using the crude rate of natural increase. So now what we can say is that, as we just wrote, K 2021 equals K 2020 times 1 plus R 2020. Just above, we were looking at the addition problem where I was looking at K 21 and then this one and then this one. So we can do the same thing here. We can say that K 2020 equals K 2019 times 1 plus R 2019. And likewise, K 2019 equals K 2018 times 1 plus R 2018. All the way back to K 2001 equals K 2000 times 1 plus R 2000. Notice that we can combine all of these things. Here's a K 2020, here's K 2020. Here's K 2019, and there's a K 2019. So we can do a substitution. We just get a recursion, and we can describe the population in the year 2021 as the year, we're going to start with the population in the year 2000 times 1 plus R 2000 times 1 plus R 2001 times 1 plus R 2002 all the way up to 1 plus R 2020. How many of these terms are there? There are 21 of these terms. So what we've done now is we've described the population in any year as the product of a series of terms. Let me say this, let me write this down. This is a little bit long to write. I'm going to rewrite this as K 2021 equals the population in the year 2000 times the product. You know this notation, that's pi, capital Pi for the product. From, let's see, of 1 plus R sub I, where I equals 2000, up to 2020. So we can describe this as a product. This is called a multiplicative model. Let me actually, I can be more general. I think I can say that K in the year T equals K, let's see now, in the year T minus N times the product of 1 plus R sub I from I equals T minus N up to T minus 1. And this multiplicative model is very common, and it is so important, I'm going to draw a box around it. I try to remember to draw boxes around important things. And this is an important model because we use it quite a bit, and this is called multiplicative. This describes multiplicative growth, or sometimes we call this geometric growth. So this is the famous geometric growth that Malthus talked about in 1798. Let me point out a couple of other things here. We could, this describes the population in the year 2021 as the population in the year 2000 times the growth rates in those years. Suppose we had future growth rates we can actually project forward, so we could say K of T plus N, N years in the future, equaled K now in this year. And if we had what these growth rates were, if we were prescient, if we could look forward and see what those growth rates would be, then we could have 1 plus R sub I, where I equaled T up to T plus N minus 1. Okay, so this is the same model as same multiplicative model. But we're projecting into the future. And if we get a chance, we'll talk about how we might do this projection into the future. Projecting into the future. Let me, as long as I'm here talking about this, I think we could do one more thing. And that is, we can take the box in red and we could say that KT divided by this string, this product of all these 1 plus R's and I's. I'm not going to, maybe I should say T minus N up to T minus 1. That thing is going to equal KT minus N, and I'm remarking about that because this thing is a way to go backwards in time. So we can go backwards in time. So if we knew what the growth rates were in the past, we could deflate rather than project. We could shrink backwards and find out what the population was at different years in the past if we knew what the growth rates were. We just do a division problem rather than a multiplication problem.